In this video, we're going to talk about two types of radical reactions that are very useful in organic chemistry. So the first one is going to be addition of X2, and the second one is going to be addition of HX. Both of these are going to be useful. We've already seen kind of additions of X2 and HX to alkenes, but we'll see how we can utilize this in a radical-based mechanism to get different kinds of reactivity and regioselectivity that we would see from normal heterolytic type cleavage of bonds. So let's first look at the addition of X2. So we've seen X2 addition to alkenes. In this case, we're going to be looking at instead X2 addition to alkanes. So the overall reaction is we have RH, some kind of alkane, plus X2. And this is usually initiated by heat or light, which I'll abbreviate as H nu. Most radical-based reactions will be initiated with light or heat. Heat's usually on an industrial scale, light usually ultraviolet type of light in a laboratory type setting. So what the net reaction we get is substitution of H and X, so we end up with Rx plus HX, an equivalent of acid. Now when we're looking at the X2 that we would use, fluorine, F2 is going to be more reactive than chlorine, which is going to be more reactive than bromine, which is going to be more reactive than iodine. And that's because that's directly resulting from the strength of the bond. So the F2 bond is fairly weak, the I2 bond is fairly strong. Usually when we're doing these reactions, we're really only dealing with Cl2 and Br2. F2 is too reactive. It's exothermic to the point that it really overfluorinates compounds and often gets quite explosive. I2 is not really reactive. It's fairly endothermic and takes too much energy to make this reaction very viable. So there's three steps when we talk about a reaction mechanism for radicals. So the first one is going to be called initiation. The second one is going to be called propagation. And the third one is going to be called termination. And each of these steps has distinctive features that denotes one step from another. So in an initiation step, we have a pair of electrons that splits homolytically, which is going to form two radicals. So you go from a neutral paired electron to two radical species. Propagation is when a radical reacts with a non-radical to form a new type of radical and a non-radical species. And termination is when two radicals recombine. So they'll recombine to form a non-radical species. So all radical-based mechanisms will always proceed through these three steps: initiation, propagation, and termination. So let's first look at the mechanism for X2 addition to an alkane. So let's look at a simple example. So for instance, we can look at the chlorination of methane. So we add Cl2, and I'll say we do this in light. And this will end up with CH3Cl plus HCl. So let's look at the three different types of steps in this radical-based mechanism and examine what happens mechanistically at each step. So the first step is going to be our initiation stage. So in initiation, remember, we have a radical break heterolytically, or homolytically, to form two radical species. So in this case, the species that's going to break homolytically is going to be Cl2. Now this is initiated by heat or light. In this case, I indicated that it's initiated by light, but on an industrial scale, this may be initiated by high heats. So we have our Cl2 split homolytically to form two Cl radicals. Very unstable. This is a 7-electron species. These are very reactive because they are 7-electron species. 7 electrons. So they can continue on to the next stage of the mechanism, which is propagation. So in the propagation phase of the mechanism, we have a radical, which we've just established as Cl dot, which is going to react with non-radicals to form new radicals in a non-radical species. Usually there's multiple steps in this type of in the propagation phase, and what we're aiming to get is, this is the cycle that happens. So we'll start with a radical, it will react, and it will generate new radicals that will then continue the cycle. So let's examine how that happens here. So in this case, we have Cl dot, that's our radical. It's going to react with an equivalent of methane. And what we'll have is we'll have what's called H dot abstraction, meaning we're going to take that radical and abstract it from the CH bond. If we're tracking where this goes, we form an equivalent of HCl, and we form an equivalent of C dot, so methyl radical. Methyl radicals, as we saw, are very unstable. We can see here we formed the HCl that we see in the product, but how do we form the CH3Cl? So the CH3Cl is going to come from another step in the propagation, which is going to be Cl dot abstraction from Cl2. So we have our methyl radical abstract to Cl dot from Cl2, resulting in a new CCl bond. There's our methyl chloride, and another equivalent of Cl dot. And what we see, and this is common for radical-based mechanisms, that Cl dot just goes right back into the cycle and reacts with another equivalent of methane. So this is called propagation because we're generating a new equivalent of radical that can go through the cycle once again. So these reactions are often chain reactions, and they often occur very fast, according to the structure, but they often occur with unwanted side reactions because this goes so quickly. So the final stage in the reaction is termination. Again, the three phases of a radical-based mechanism are initiation, propagation, and termination. And termination is just any two radicals recombining to form a non-radical. So we can really take any two radicals that we see in this reaction and combine them. So we have ClCl combining, which would form which would reform Cl2. So that would just go back to the beginning. We can have Cl dot combined with CH3 dot, so methyl radical, which would be what we call a productive side reaction because that would form our desired product. There's that CCl bond that we desire. But what we see, and this is usually unavoidable unless we have steric restrictions on our carbon radicals, what we often see is dimer formation. So we have two CH3 dots that are going to combine to form a dimerized species of the original methane. So often what we'll see is if we're using methane in our radical-based mechanism, we will often see some amount of ethane come out in the products because of an unwanted dimerization that occurs in the termination step. Now, this reaction is often difficult to control. If we look at this CH3Cl, this can react further with Cl dot, so often we get a mixture of products. In fact, we get CH3Cl, we get CH2Cl2, and we get CHCl3 and CCl4. So we get a mixture of these four products as well as the dimerized ethane that comes up in the end. And it would be simply a factor of separating these products out from the end, usually based on distillation or density, that you could separate these four products out. So if we're considering reactivity or regioselectivity of these reactions are going to form where the most stable radical forms. So for instance, if we're going to chlorinate this species, there's only one spot where we can chlorinate, and that's right here. So we would get, if we're talking about the monochlorination product of this reaction, we would get a single chlorination there. If we have higher alkanes, so for instance, butane, and I'll say this is initiated by light, we have two products that can form. We can form at the terminal position, so we can chlorinate at this primary radical, or we can chlorinate at this secondary position. So in fact, we would get a combination of products. But since this involves a radical intermediate, we would see an overwhelming representation of the secondary chloride because that secondary radical is going to be much more stable than the primary radical. So we might see a distribution of something like 75-25, but we would still see a distribution because these are all possible. If we include resonance in this structure, so say we're doing this with bromination, we'll do this with light. Again, we saw that there's three radical intermediates that can form. We can form this radical, we can form this radical, with the secondary. And then remember, this exhibits resonance, where we have another primary radical that can be accessed. So we have three possible products that can form. So those possible products would be the terminal bromide, the secondary bromide, and the other terminal bromide. And if we're looking at which one of these would be most, if we were to rank these in order of most abundant to least abundant, we'd have this secondary as the most abundant. This one, which exhibits allylic resonance, would be secondary. And then this one, since it's just a primary radical, would be the least abundant system that occurs here because it is the least stable in this case. So the secondary reaction is one we've actually already seen, and this is addition of Rx or HX to alkenes. So we already saw this reaction in chapter 8, where if we add HX to propene, we will get Markovnikov addition to the more substituted position of the alkene, meaning that we get a secondary alkyl halide versus a primary alkyl halide. We also saw in that chapter if we add HX in the presence of peroxides, we will get anti-Markovnikov addition. And here's when we're going to explain why this happens. So let's look at the three stages of the reaction mechanism and explain why we get anti-Markovnikov addition if we are in the presence of peroxides. So again, our first step is initiation. In this case, this has to be initiated by heat or light. So we'll say that that's initiated by heat. In this case, the initiation step is going to be the homolytic cleavage of the OO bond in the peroxides. So similar to the Cl-Cl bond, it's fairly weak. So this OR bond will form two O radicals. And that is the initiation step in this case. Now our propagation step is going to be, again, reactions of radicals with non-radicals. So the first step that we can do here is we can do an H dot abstraction from HX. So we can have an H dot abstraction. We get the O dot reacts with H and we form X dot. So what we'll see is we always get equivalent of alcohol in this type of reaction. We will get an equivalent of alcohol for every equivalent of peroxides that reacts. And now we formed X dot. Finally, we can have X dot react with the alkene to form a new radical species. Now we have a choice here. And I won't draw the second arrow. We have one arrow that can push onto the secondary position, and we have another arrow that can push onto the primary position. So let's examine those two species. So the first species, and I'll draw it in red, would be forming the secondary radical with X at the terminal position. Now in blue, I'll show the other option, which is X at the secondary position and a terminal radical. In examining these two species and based on the types of reactivities that we've seen already, we can already tell that this secondary radical is going to be more stable than the primary radical. So the secondary radical with anti-Markovnikov addition of the X is what's going to be preferred in the formation of this radical. Finally, and I'll just draw this in the same step, we have another equivalent of HX that can form, and we'll have H dot abstraction once again to form the desired product. So there's our X and there's our H, and you'll see that that X dot can then go, this is now X dot, this can go back and react with another equivalent of alkene and continue the cycle. So there's our chain propagation. Finally, in our termination stage, we will have any two radicals recombine. So you can have X and X, which would get X2. You can have RO and X, which would give you ROX, a strange species, but it can form. And finally, and I'll draw this over here, you can get, just like we saw the dimerization occurring in the previous example, we can get dimerization occurring in this example as well. So again, we do get dimer formation regardless of whether we want to or not, and that's just because we have radical recombination in the termination step that is frankly unavoidable, but often can be separated out at the end based on density, melting point, solubility or distillation.